Same idea. F of x equals 2x minus 1 if x is less than or equal to 1. Or f of x equals 3x plus 1 if x is greater than 1. So right now I know that something's happening at the line x equals 1. That's where the things are going to shift themselves around. So I start with my first equation, 2x minus 1. What's my y-intercept? And my slope? 2. Up 2, right 1, 2, right 1. Or down 2, left. And for that line, do I need a solid or an open dot at 1? I need solid. What side am I going to erase? The greater than 1 or less than 1? Greater than 1. Very good. Everybody agree that I have to erase the dots going up? And I just connect the rest. Does it make sense why I was saying if you guys brought pencils today, how it's a little bit cleaner? It takes an extra second or two to go ahead and draw out the whole lines, but then you go back to see what you have to erase. I always thought there was a little bit easier method of doing it instead of just trying to go right to the spot and walk it from there. Same thing, 3x plus 1. Where do I start that one? At 1. I'll change colors here. And then I walk my slope of 3. Yes, it will be an open dot. That one's going to be an open dot, and when I start walking my slopes, I usually just make them just the dots to start. But then when I'll go back, I'll just go back and do this and erase that one there. You just kind of overlap it like that, and that's fine. And then I just got to connect the lines going up. Some real easy examples of like different ways things happen like this. Like I said, overtime, when you're getting paid time and a half. Taxes are different levels as you earn different income, the tax rate increases. So you see that as a piecewise function. If you're buying things in bulk, you get a price break, so that's a piecewise function. Sir?
Why does it start, the red one, why does it start right there? Why doesn't it start on the
Because it's domain specific. The regular graph, if you will, would start at 1, you walk your slope and go on your merry way. And it would go the other direction as well. But since I'm only wanting to see this graph for this domain, for when x is larger than 1, that's why I only started here.
Also, if there's like 2, we start there.
Exactly. It's exactly right. And sometimes it might not line up on the actual slope, on the point of the slope where we were walking it. Sometimes it's off. Remember that first example where the 5s were in between? But you can kind of guesstimate it where it's going to wind up. Okay? These are just domain-specific style problems. Mr. West?
Wouldn't the y1 be in the negative area instead of being positive where it starts?
Which one are you looking at?
Because the top one, since it's a negative one, wouldn't it be in the negatives? Wouldn't
Oh,
it start
that's
in
the intercept is the negative. The slope is still positive.
I don't
Remember, the slopes are the coefficients of the x.
know, but why does it start in the positives, like where you read it from? On the graph. On the graph.
Because of the domain.
Oh.
Because of the domain is telling you that you only want to look at that graph when x is smaller than a positive 1. So it's going to be starting at positive 1, and I'm going to look at everything to the left of it. For all the domain, remember the domains are your x values, so the domains, I'm looking at all the domains going to the left. All right. Mr. Connors?
Why do you do it, man?
Which part? Let me put another one up and I'll walk it through again even a little bit different, okay? That's a little bit more, yeah, we'll try this. No, we'll do this one. Okay? We'll worry about the cut aparts. It's not that much crazier. I've got two graphs. I have f of x is either 3x plus 2 or x minus 1. The domain that I'm worrying about here for the first graph is if I only want to see that graph on the graph paper for all the x values that are less than or equal to 3. The other graph will be shown for all the x values that are greater than 3. So right now I know that this line, 3x plus 2, is going to be everything going to the left of 3. Because those are all my domains that are smaller than or equal to 3. This line will be everything going that direction. All right? So 3x plus 2, what's your y-intercept? 2. What's your slope? 3. So I'm just going to start at 2 and walk my slope. Up 3 over 1. Up 3 over 1. And so on. Or down 3 over 1. Now what I have done is just filled my entire coordinate with all the possible dots that just fit on my grid. Do you agree with that? Now, what I want to do is go to where x is 3. It's right here. That means it hits that line about here, if I were to continue to walk it up. It's a little bit off of the line. It didn't land on an exact spot that I counted on my slope. But can you kind of guesstimate that it's about right there? Now, it's less than or equal to. Should that be an open or a closed dot? Closed. And now which way are numbers smaller than 3? To the left or to the right? Correct. So I just go like this. I've just graphed that portion of the line that's dependent upon that domain. All right? And then I do the exact same thing with the next line. What's the slope of the next line? What's the y-intercept? -1. So I start at -1. And I'm going to walk my slope of 1. Okay? Go back to where it's telling me that something happens. Something happens when x is greater than 3. Right here again. Should that be a solid or an open dot? Open. I'll make this. And what way should I be going? To the right or to the left?
To the right.
And there's my piecewise function. And then I just go back and erase the other dots. That's it. You're graphing two lines on the exact same grid like you have in the past. The only thing that has changed is that you have to go back and erase portions of the line that don't fit in with the domain. It's restricted. That's why I kept saying domain restricted or specific. Okay? You want to try a couple on your own? All right. You don't like these? These are easy. These are fun. Because they're easy and fun? Oh, all right. Well, this first one is a little bit different. They can be. Well, what's nice is that for some of these things, what do you guys all have in front of you? You guys all have calculators, right? No. Do you guys all have buttons on your calculator that say y equals? Do you happen to remember that if you press y equals and you type in that calculator, what happens if you press the table?
It gives you a table.
It gives you a table and it tells you what your values are, doesn't it? Could you plot those values? And then could you go back and erase things? That's exactly what you do. Let's take a look at that example I have there. I believe this is the very first example. Here's what I would do. Here's what I would do. I would take out my calculator, especially if I'm having problems graphing. So let's walk you through how you would pull information from your table to plot. Well, just leave it in the pile. Remember, I don't like to count. There we go. And I'm going to type in that top equation, x plus 5, in the y equals. Okay? And then just go right to my table. Does everybody remember how to find the table? Second graph. Very good. Now, here's what's really nice. I use the computer to do that. By looking at just the table, by just looking at the table itself, I can just cheat and pull it right on the board here instead of moving it up. I know my ordered pairs. X is -4, y is 1, -3, 2, 2, 3, -2 and 3, and so on and so forth. And I can plot those points real quick. On this grid, it's not marked off by numbers at all. Just assume that everything is 1. I think it's pretty easy to think that. So if we go to plot that first one again, and I have y-intercept there, and I'm just going to go and backtrack my slope. That first one is really easy to do. That's why I wanted to show you an easy example of how to read the table for a linear one. Now I look at it, and it's domain specific for which values? Everything's smaller than -2. So I go to -2 on my x, and will that be an open or a closed dot right there? Open, very good. So I'm just going to make an open dot, and I need to go smaller, which means I got to go this direction. Go back, erase. Not so bad? Now the fun part. Oh, I lost you. You had expression face. All right. Go to the other graph. The other graph was x squared plus 2x plus 3. We haven't done a quadratic yet in these calculators. I'm assuming you guys can figure that out. X squared plus 2x plus 3, I believe. Is that right? It was plus 3, right? Yeah. Go to my table right away. And once again, I have my table ready to go. I'm just going to pull this onto the board because it's easier for me to transpose it then. I know that I have to be larger than -2, so I'm just going to start at my -2 value. 3. My -2 value is at 3. Herein lies a silly situation. I know I have to start this here at 3.
Oh, so wait, if that was on the test,
And that's
like, give us the question when it has, we have to call it in.
That's exactly right. What happens here is that the graphs change and they actually intersect at the same point. That's okay. When that occurs, you just fill it in as a solid dot, and that's not a problem. Okay? It's not a problem because it's telling you here that the domains, it's okay for that to occur. It just happens that every once in a while, you'll have the intersection of the two lines occur where the domain changes. Where it changes graphs, if you understand what I mean by that. So when that happens, you fill it into a solid dot and just continue your other graph. So I was at 2, 3, excuse me, -2, -3, or +3, -1, and 2. 0 and 3. 1 and 6.
Oh, you're just reading off the table?
I'm just reading it right off the table. That's exactly what I'm doing. There's no reason for me to be doing all this extra substitution at all. That's why we have the table function on the calculator to allow us to create these points, to create the tables. Because now I know I have a curve, like Mauner said, and I just go up like that. And I've created a funky looking graph by being domain specific. I pieced together two graphs, one grid, with a change at -2. Okay? Not bad. Do number 2. Do number 2, same idea. It's got the x squared in it. Give you guys a second to get going where we're at. 2x plus 1. I start at 1 and I walk my slope of 2. I look at my domain. I want it to be only for when x is greater than or equal to 1. So I go over here to the 1. It's a solid dot, and I need to go up. Erase the rest. For the quadratic part, it's x squared plus 3. Now, if I'm not mistaken, that means at 0, it's 3. At 1, it's 4. Which means at -1, it's also 4. At -2, it'll be 7.
Is it fine if you use the calculator?
It's absolutely fine. It's absolutely fine. This one I thought was a little easier. Just for instead of me going back and typing it all in, I was just going to show the curve real quick. And now, the reason why I have an open dot at 1 is because can't be equal to 1. And I come back with my curve. And that's it. So you see how you can mix these things with linear and quadratic? It does not matter. It still all goes together. It still all goes together. All right? I really kind of wanted to be able to get into writing of the equations on these things today, but I guess we'll get to that tomorrow. You know what? These are nice note worksheets and whatnot. Why don't you finish the last 4 graphs on this, and we'll call that for our homework for tonight, and then we'll continue this tomorrow with writing the equations of them given a graph. Okay? Yeah, you know what? No, yes, yeah, please. No. I forgot what class I have next. Yes, I have algebra. I've got you guys again next hour. So yes, you can leave my desk.
Is that a final answer?
Maybe.
Okay.
Yeah, guys, like I said, there's 4 more of them on that sheet. Just do those 4 for tonight, and we'll call it a day, and we'll talk about writing the equations given graphs tomorrow. When we do that, we will not have curves. Yes, ma'am. What's that? I'll give you a second. You just stop to go fast.